today's lesson. Today we're going to look at the beginnings of solving trigonometric equations. So the first thing I need to do is define what I mean by a trigonometric equation. A trigonometric equation is any equation involving a trig function of a variable. Something, for example, like this. There's a trig function, and specifically I'm going to try and change the y value and make this perhaps 0 equals sine x. Notice I'm taking sine of a variable, and this makes it a trigonometric equation. And this can be solved. What we would be asking for example, in this one, is what values of x make this equation true. In other words, sine of what angles makes this equal to 0. So if we were going to solve this particular trig equation, probably I would be thinking about the graph, and I'd ask myself, well, there's a sine graph, and if I wanted to get my answer, say, in degrees, I would make the observation that when I plug in 0 degrees, when I plug in 180 degrees, or if I plugged in 360 degrees, then the sine of each of these three angles equals 0, as is indicated on the graph. Now, this would be correct if I said, oh, we just want to have the angles between a certain limited domain. Perhaps I was saying, well, let's say x is between 0 degrees and 360 degrees. Then this would absolutely be the three solutions. But what if I said, oh, we're not going to restrict the domain. We want all the answers. This is what we call the general solution. And for the general solution, I need to come up with some way to say, well, it's like these three, except it keeps going forever in both directions. What we could do there is suggest, well, these solutions seem to occur every 180 degrees. So what I'm going to do is say, why don't we just take multiples of 180, and that would be my general solution. Multiples of 180, where n here belongs to the set of integers. Now, if you think about it, one integer, for example, is that n itself is 0. 0 times 180 gives us the 0 degrees. If n was 1, 1 times 180 gives us 180 degrees, and so on and so forth. And you can see we're going to capture all the solutions, every single one of them, and there's billions of them, with the general solution. So this is what we mean by a trigonometric equation, and I've done an example here where we've solved over a limited domain as well as for a general solution. Now what I'm going to do is take that same equation and do some minor modifications to it and see how that would affect our answers. Suppose, and we'll just get a fresh start here, suppose we had a very similar equation, except I was going to make one minor change, perhaps something like this. Instead of sine x equaling 0, maybe I put a 2 in front of the x. Okay, so the same kind of equation, definitely a trigonometric equation, but we've got this change happening here. And what is that change? It's very important for us to identify what this 2 actually does. Well, it takes the horizontal element of the graph and multiplies it by a factor of 1 over 2. So what we have happening here is that horizontally, everything is multiplied by 1/2. It gets compressed by a factor of 1/2. So what we do here is we say, well, let's ignore the 2. Let's find the solutions for this. And then what we'll do is take those solutions and multiply them by a factor of 1/2. So if we think back to the previous example, the solutions to this trig equation were 0 degrees, 180 degrees, 360 degrees. Indeed, we had the idea of multiples of 180 degrees. Well, if I squish this up by a factor of 1/2, then these are going to change a little bit. 1/2 times 0 is still 0. 1/2 times 180 would be 90 degrees. 1/2 of 360 is 180 degrees. Now, because in my original example, I said the domain goes from 0 up to 360, you can see what's going to happen here. If this pattern continues, I'm essentially going up by 90 degrees now. So the next one would be 270 degrees, and the last one would be 360 degrees. So in fact, I would end up with 5 solutions over the domain from 0 to 360 degrees. Now, what about the general solution? That one's in a sense a little easier because all we have to do is say, take this and multiply by 1/2. So the general solution becomes n times 180 times by 1/2, which would be n times 90, where n is still any integer. So a little bit easier to actually work this one out. So that's the kind of modifications, transformations that might occur in some of these trig equations. And all we have to do is go back to kind of the stem equation and say, well, what were the solutions, both general and specific, and make that kind of modification, that transformation on our solutions. Well, let's look at another example and put a few little changes in it. Like maybe it doesn't equal 0. Let's have a look. In the next trig equation that I want to solve, I think what I'm going to do is something like this. 0 equals cosine of 2x minus 1. So a little bit more happening there. And we also have changed from working with sine to working with cosine. Okay, let's see what we have here. Well, what I'm going to do first of all is bring the 1 over to the other side. So what I'm wondering is, cos 2x, when does this equal 1? Well, again, I think of the value of 1, and I think of a related function here, kind of the stem function, which would be, when does cosine of anything equal 1? So let's have a look at the graph, and that's probably the easiest way to identify when does cosine equal 1. And the cosine graph, you will recall, looks something like that. This time I think I'm going to work in radians, just so that we don't get rusty with our radian measure. So this is 2 pi, and this is 0. Those are the two places here and here where I've identified that cosine reaches a level of 1, where it equals 1. So what I have to do is once again say, but this isn't cosine of x. It has a certain modification. In fact, it is being compressed yet again horizontally by a factor of 1/2. So what I'm going to do is take these solutions, radians, and 2 pi in radians, and multiply them both by 1/2. So what do those now become? Well, 0 times 1/2 is still 0. And 1/2 times 2 pi just leaves us with pi. So if we have a restricted domain, it would appear that we have modified these to 0. The 2 pi becomes pi, and very likely we would also have the 2 pi. Now I'm going to confirm that when I go to the general solution. The general solution here, well, if we look at what's happening here with 0 and 2 pi, it would seem that every time we start a cycle and finish it, that's where these solutions occur. That's when we hit 1. We would expect another cycle to continue, and again hit 1. So every time we go a distance of 2 pi, we're going to get another solution. So we're looking at multiples of 2 pi. But once again, this is only kind of the stem graph, and we have to remember that we are compressing it by a factor of 1/2. So 1/2 times this would be canceling the 2's, and we're looking at multiples of pi. So we are now confirming that 2 pi is indeed part of that. So if we had said let the domain be 0 to 2 pi, then we would find the solutions are 0, pi, and 2 pi. If, on the other hand, we wanted all solutions, or the general solution, then we would say n times pi, where n is an element of the set of integers. And that would give us our solutions. Okay, let's look at one last example. And then I think that's probably good for a start as to solving trigonometric equations. This time the example I think that we're going to try to solve will look something like this. Sine of 2x, and when does that equal 1 over root 2? And again, we'll solve specifically for a certain domain. Usually they make that very clear in any of the questions, and they would say for x between 0 and 2 pi. Sometimes you'll see that it is strictly less than 2 pi, so that you can't actually include the 2 pi, but I like to include it, so I'm going to go with between 0 and all the way up to and including 2 pi. So I start off and ask myself, well, in the stem equation, sine of what angles equals 1 over root 2? And these numbers, 1 and root 2, make me think of my special triangle. Well, one of my 2 special triangles. And the special triangle that I think will help us here is the isosceles right triangle that has a length of 1 for each of the legs and a hypotenuse of root 2. And that makes me think, well, the sine of this angle down here, which is pi by 4, or 45 degrees, that angle has a sine of 1 over root 2. So certainly one of the solutions for the stem equation is pi over 4. However, there is another solution between 0 and 2 pi, and we get that other solution by our old friend the cast rule. Now the cast rule tells us that sine is positive, which is what we have happening in this equation, in this quadrant and this quadrant. So we want to construct our reference angle of pi by 4 into these 2 quadrants. So we have pi by 4, and over here we're going to construct pi by 4 as a reference angle. So I'm going to build that up from the x-axis. Now that's an excellent picture of this angle, but it's not named appropriately. We don't name them by starting here and saying, well, you kind of build up from the x-axis up pi by 4, and there it is, and you're in this here quadrant. That's not the way we name them. We name them by starting at the initial arm here and swinging counterclockwise. So what is the supplement to pi by 4? Well, here's one way that you can kind of figure it out. Think of it this way. From here all the way to there is pi. Or if we like, we can think of it as 4/4 of pi. In other words, 1/4 2/4, 3/4, and 4/4. So we hit here at 3/4 pi. So that's the other angle. 3/4 pi. Now remember, so far we've only been solving the stem equation. So what I now have to do is say, wait a minute. We actually have a 2 in front of the x. And as we've seen with the previous examples, that means that each of these needs to be multiplied by 1/2 to compress it horizontally. So if I multiply each of these by 1/2, then this will become pi over 8. The next one will become 3 pi over 8. And undoubtedly, I'm going to have another solution and probably 2 more. Now I'm going to wait with these and then get my general solution and then figure out exactly what these are working off the general solution. Some people like to just look at this and identify that the pattern seems to be 1/8, 3/8. So probably we're looking at 5/8 followed by 7/8. Now that's a pretty good educated guess, I'd say, but let's make sure about that. In the general solution, we would take each of these starting points, and if we work with pi by 4, we want to make sure that that happens a full cycle later. So we're going to add to the pi by 4 multiples of 2 pi. Okay? Sine, after all, in my stem equation, has a period of 2 pi. So I'm going to take this number and say, well, multiples of 2 pi, I'll capture all of those solutions. And the same thing would be true of 3/4 pi. So 3/4 pi, we would have 3/4 pi plus multiples of the period. Now when we modify these, we take the 1/2 and multiply both elements of it. So we get pi by 8 plus, and 1/2 would cancel the 2. So we're going to get multiples of pi. And over here we're going to get 3/8 pi plus multiples of pi. So these are the general solutions. And so far we've only had 2 specific solutions, and we think there will be more on the way. So let's have a look. If we add multiples of pi here, an easy way to think of pi is to think of it as 8/8 pi. So I'm going to just change this here a little bit. It's still n times pi, or multiples of pi, but I'm going to write it like this. Multiples of 8 pi over 8. Now why would I do that? Because then it's very easy for me to see that I'm going to be adding 8 to the one in front here. So I take 1/8 plus 8/8. So if n was 1, for example, and that would give us 9/8 pi. So, very interesting. Those who jumped the gun and said 1, 3, and 5, albeit they had their reasoning, would have been mistaken. Same thing I'm going to do over here now is say, well, if we go a full period later, that would be like adding 8/8. So I would expect to see 11 pi over 8. 3 plus the 8 to make 11/8 pi. Now, just to confirm that there are no more solutions, if I added 8 to either of these, for example, if I added 8 to the 9/8 pi to go another cycle, I would get 17 pi over 8, and that would be beyond 2 pi. So after all, 2 pi in my domain here would be if I had 16 pi over 8. So I can't go more than 16. That's kind of the upper boundary. And of course, adding 8 to 9 makes 17. So I'm outside of the domain. So this is it. These are my 4 specific solutions, and these are my 2 general solutions. And with that, I'm going to stop with today's look at solving trigonometric equations. We'll be looking at more solving of trigonometric equations, but not today. Catch you later.